So we're going to talk about Lab 9, and we've had a couple labs on thermodynamic equation, um, calculating the terms in the thermodynamic equation, and we've also talked about the frozen wave hypothesis and used that in the vorticity equation to help us easily and quickly calculate the local time derivative. And we've also talked about the quasi-geostrophic approximations and used that with the vorticity equation. So we're going to continue that and use the quasi-geostrophic version of the thermodynamic equation along with the frozen wave hypothesis, and see how we can use that to calculate the intensity of the vertical motion, the rising and sinking motion, for a snowstorm that occurred a couple years ago. You can check the Weather Service up in Chicago for information on that storm. And the data are available on Scholar. So the ThinLink desktop.scholar link will allow you to access the data. And so you want to start a terminal, and you can see there's a couple commands for this lab that are a little bit different. So we're going to actually customize the restore file that will plot the temperature advection for the quasi-geostrophic thermodynamic equation. And so you need to type this copy command in the terminal. So it goes copy space /scratch /scholar /m /me baldwe /EAPS433, and then QG star 700, and then space home /restore / and now copy those into your restore directory. So there should be QG omega and a QG temp advec 700 restore file that you'll be editing, and then you want to source the setup file. So we can type that in: source /scratch /scholar /m /me baldwe /EAPS433 setup _433 .profile, and then you can start nmap2. And it's a good idea to use an ampersand after nmap2. That'll run this in the background, and that will allow you to still type in the terminal, which you'll need to do for this particular lab. So I'm going to go ahead and exit out of this, and you see that the lab goes through some background material, sort of covering the frozen wave hypothesis, which we've talked about before, and the QG thermodynamic equation, and how you can combine these together to come up with an equation for omega. Omega is the vertical velocity in pressure coordinates, and when omega is less than 0, it's rising motion. This ends up being a fairly simple equation. It's -1 times the temperature advection by the system relative geostrophic wind divided by the static stability parameter. And this is a very similar approach that we use in Lab 6 with the QG vorticity equation to figure out the divergence. So the lab kind of goes through various steps to figure out the system motion vector and temperature advection, and then modify the restore file to include the system motion and do some calculations. So there's a worksheet with this lab. So type in the answers to the questions provided, and turn in this worksheet. So it's most helpful if you export this as a PDF file before you turn it in on Blackboard. So to provide a little bit of background on the quasi-geostrophic thermodynamic equation, and we're actually trying to get to the quasi-geostrophic omega equation, so I'll go ahead and introduce that today as well. This combines the thermo and vorticity equations to come up with an equation that allows us to diagnose vertical motion when we can assume that we're dealing with synoptic scale flow. So just to review the frozen wave hypothesis, this is a way for us to estimate the local time derivative using sort of a pretend advection by the motion of the system. And so here is C sub x and C sub y are the east-west and north-south components of the system motion vector C. So if we have, say, a surface cyclone that's moving, and we can track it from one time to the next, and we see its motion is, say, 300 degrees at 30 knots. So basically moving from the southwest towards the northeast. We can use this and calculate an advection by this vector C. So minus C dot grad T would be the temperature advection by the system motion itself. And so if we measure the gradient along the direction of the system motion, so here we measure the distance between two isotherms and make that measurement parallel to this vector, this C vector, we would see that the temperatures increase, in this case, between 5 and 15 degrees C over 100 nautical miles. And so we can use our simple advection calculation method, take this delta T divided by the delta X, and then multiply it by the wind speed, and then multiply that by -1, and we would get a -3 degree per hour local change in temperature just due to the motion of this system. And that makes sense. If this was just moving off towards the northeast, then we would get these lower temperatures moving towards our location here. So this is using a center difference method to estimate the temperature gradient at this little plus sign. And that's a way we can use the frozen wave hypothesis to estimate the local time derivative, partial t dt. Well, we can combine that with the actual advection and determine the advection by the system relative flow. And in this case, we're interested in the geostrophic wind, since the geostrophic wind does the advection in the quasi-geostrophic equation set. So when something like EAPS433 or GenPack calculates temperature advection using, say, a system motion vector that we can break down into east-west component of 5.3 meters per second and a north-south component of minus 7.1, then we would plug it into our GDP fund like this. We would set up another vector. This VECN north, or VECN, is a vector relative to north, and these are the x, y components of that vector. And so GenPack EAPS433 uses meters per second for the winds, and then we would subtract that from the geostrophic wind. And so this V sub is a vector subtraction function, and it's subtracting the geostrophic wind and this vector, the C vector. And so this calculation would be giving us this function right here. So the system relative geostrophic flow here is Vg minus C, and then we're going to take minus that dotted into the temperature gradient, and that gives us the advection by the system relative geostrophic flow. Well, often what we need is just -1 times this. So we'd have to multiply this advection times -1 to get what we're after. So we're dealing with the QG thermodynamic equation. And again, just to review this is a simpler version of the full equation. And we're neglecting terms that are small for synoptic scale flow. So we define that as a Rossby number of roughly 0.1. So we do have some acceleration, but it's relatively weak. And that's the case if we're looking at weather systems that have a wavelength on the order of 1,000 kilometers and wind speeds on the order of 10 meters per second in the mid-latitudes. So if the Rossby number is 0.1, it's almost geostrophic. Perfectly geostrophic would give you a Rossby number of 0, and it's called quasi-geostrophic, or QG for short. And so if we look at that QG version of the thermodynamic equation, we have the full thermodynamic equation here. We're using pressure as a vertical coordinate, and we've rearranged the terms so that we have our we're basically trying to find the local time tendency. So that's equal to the temperature advection. So it's minus u dt dx minus v dt dy is the horizontal advection. And the work and vertical advection terms can be combined into a single term. So here it's omega times minus t over theta d theta dp. And this is a sort of static stability parameter. It will be a positive number when the atmosphere is stable. And then we have the added heat term, or the latent heat term, at the end. So the QG version is a simpler version. You can see there's no added heat term, so it's adiabatic. And the advection is being done by the geostrophic wind. So UG and VG are the advection terms here. The other assumption doesn't really show up in this form is that this static stability term is constant horizontally. It varies in the vertical, but it doesn't vary in the horizontal. So we can rearrange these and solve for omega. And that's basically what we're doing in this lab. So if we do that and we use a frozen wave hypothesis, we find that omega is -1 times the temperature advection by the system relative geostrophic wind divided by the static stability parameter. So thinking about this gives us a really nice way of kind of understanding why we get rising and sinking motion. If the atmosphere is stable, the static stability parameter will be a positive number, and again, we're assuming it's constant in the QG world here. So this is just going to be a constant. And that means that omega is going to basically be the opposite sign of the temperature advection, at least by the system relative flow. So if we have warm air advection, this numerator would be positive, multiplied by -1. That would give us negative omega, and that's rising motion. So we should see a relationship between rising motion and warm advection, or sinking motion and cold advection, if we analyze this with real data. So let's take a look at an example. This is looking at 700 millibar heights in yellow, and temperatures are the dashed blue lines. And we can look at this and try to find some areas of fairly strong temperature advection. So we can see some pretty good cold advection in the northern plains, and another area of cold advection just off the east coast, and some pretty good warm advection in the northeast with this flow going across these isobars. So if we actually have GEMPAC or Nmap2 calculate the advection for us, we can see, sure enough, we've got good cold advection in those areas and warm advection just to the east of this cyclone. We'll notice if we look at the omega, that's also where we've got good rising motion. These negative omega values are pretty much coincident with that rising motion, or that warm advection that we just looked at. And there's sinking motion, positive omega, down in the Carolinas, where that cold advection was showing up. And notice on the satellite, we've got this cloudy conditions where the rising motion is occurring, and forecast of precipitation in that area as well. But down in the Carolinas, this is where we've got sinking motion. There's no precip, and it's very dry air. The infrared satellite shows this pretty nicely as well. So you can see, where we've got the strong rising motion is where we have the deep clouds and the cold cloud tops. So there's likely a lot of precipitation going on in this area. So that's really the point of this lab, is to see this connection between temperature advection and rising and sinking motion. And this sort of transitions into the what's called the omega equation, the quasi-geostrophic omega equation. And the foundation for this is the thermal wind balance, which is pretty much falls out if you assume the atmosphere is hydrostatic and geostrophic. So if we take the vertical derivative of the geostrophic wind, we see that vertical wind shear is directly related to the horizontal temperature gradient. And that's what we call the thermal wind, this vertical wind shear. So we can find that vertical shear basically by doing a vector subtraction between the upper level wind and the low level wind. We see that wind shear vector, and we can relate that to the horizontal temperature gradient. So if the atmosphere is in this balance, if the atmosphere is in geostrophic and hydrostatic balance, we should see in the northern hemisphere cold air on the left, warm air on the right of the vertical wind shear. And it turns out that the atmosphere really likes this balance. It will try to return itself into this balanced state, especially for large-scale flow. And so we can derive an expression for this if we combine the quasi-geostrophic vorticity equation and the quasi-geostrophic thermodynamic equation. It's sort of the two equations we've been dealing with in this class. Take appropriate derivatives of these and subtract those equations, and you get what we call the traditional form of the QG omega equation. And that's this big equation on the slide. And so, we can take a look at this. The left-hand side we usually call the response because it involves omega, and basically omega responds to the forcing. And so the right-hand side is usually what we call the forcing terms. And you can see that those involve the geostrophic wind and the geostrophic advection. So the geostrophic vorticity advection and the geostrophic temperature advection. And it's the geostrophic wind advecting the temperature and the vorticity that actually can disrupt the thermal wind balance. And when that happens, we get rising and sinking motion as a response. And that's a geostrophic flow and acts to return the atmosphere back into this balanced state, this thermal wind balance. Of sort of redefine the static stability parameter, and you can see this minus T over theta, d theta dp, and multiply it by R over P, and we sort of call this Greek letter sigma. So you can see that showing up in the denominator on both these forcing terms, as well as this this vertical derivative in the left-hand side. So let's take a look at this equation sort of term by term. The left-hand side, you can see you've got the del squared. So that's the second derivative, partial squared dx squared, partial squared dy squared, also called the Laplacian operator. And then we have a partial squared dp squared with f naught squared over sigma multiplying it. And f naught squared is a positive number. Sigma is also positive if the atmosphere is stable. So this is just a positive constant that's multiplying this second derivative in the vertical. And this is basically a 3D second derivative operator. You sort of think of it as a fancy second derivative that's operating on omega. Well, this is a partial differential equation here. We could solve this. It's not easy to do, but that's not really what we're trying to do here. We're trying to just qualitatively understand whether we're going to get a positive or negative value of omega based on the right-hand side. And usually what we do is assume that omega is wave-like, something like a sine or cosine function. And if that's the case, if we take the second derivative of a sine function, we just get minus 1 times that function. And so this big, fancy, complicated operator, we can approximate as just a negative sign. So we're negative 1 times omega. So that's what we'll do. So we approximate this as minus omega equals the right-hand side. So we need to understand the right-hand side and the forcing terms. So let's look at those individually. So the first term, we'll kind of work this from the inside out. Okay, so we see minus Vg dot del zeta g plus f. Well, zeta g plus f, that's the absolute vorticity. It's the geostrophic absolute vorticity. And then minus v dot del something is advection. And so this is vorticity advection by the geostrophic wind. That's what's in the square brackets here. And then we take minus f naught over sigma d by dp of that. Well, minus d by dp of something is basically the same as d by dz of something, right? Because pressure and height go in opposite directions. In the northern hemisphere, f is positive, sigma is the static stability parameter, that's positive. So this is just a positive constant. So basically this is saying we're taking the vertical derivative of the geostrophic vorticity advection. We want to see how the geostrophic vorticity advection changes with height. And if you think about this, since the vorticity is really related to the wind, this is telling us how the geostrophic flow is messing with the vertical wind shear and that part of the thermal wind balance. If the geostrophic vorticity advection is increasing with height, getting more positive with height, then this ends up being a positive number, and we call that positive forcing. The second term we'll look at the same way. Start the inside, work our way out. So we see minus Vg dot del T. Well, like before, when you see minus Vg dot del something, that's advection, and it's temperature advection by the geostrophic wind. Well, again, we have a negative R over sigma P and the del squared that's operating on this. So R is a constant, sigma is a static stability parameter, that's also a positive constant. P is just pressure, that's just another constant. So we can just think of this as a constant, and we're taking minus del squared of the geostrophic temperature advection. So del squared, remember, is the second derivative, partial squared dx squared plus partial squared dy squared, the Laplacian operator. And we're basically taking the Laplacian of the temperature advection, the geostrophic temperature advection, and multiplying it by minus 1. And the second derivative operator we just talked about before, we can treat it as a minus sign. So we have two minus signs, they cancel each other out. Basically, we just think of this as a plus sign. And we're basically just looking at the geostrophic temperature advection in this term. So the real simple way of interpreting this is if we have warm advection, by the geostrophic temperature advection is warm, this would be a positive number, and this would be positive forcing. Well, when we actually calculate this, we should still take the second derivative. And the second derivative actually highlights local maxima and minima. And so this is saying we're looking for locally large values of temperature advection, either warm or cold advection. And so this term is telling us how the geostrophic flow is messing with the temperature gradient, right? If we have locally large values of temperature advection, that's going to change the temperature gradient, and then that messes with thermal wind balance. So putting this all together, the omega equation, we basically have minus 1 times omega is equal to the geostrophic vorticity advection changing with height plus the geostrophic temperature advection. And if the sum of these terms is positive, that means we have positive forcing, we should see rising motion. We should see negative omega. And if the sum of the forcing terms is negative, then we should see sinking motion, which is positive omega. So this is a really important equation, something that we use a lot when we try to understand why we're getting the weather that we're observing. If we have rising motion, we should see clouds and precipitation, and this basically is telling us why we're getting that weather. There's another version of this, which we'll talk about on an upcoming lab, called the Q-vector form, where we basically rearrange those terms, do some other manipulation. The left-hand side is exactly the same, so it's this fancy second derivative operator on omega. The right-hand side is just minus 2 times del dot Q, where Q is the Q vector. And whenever you have minus del dot something, we're basically looking at the convergence of that vector field. So we call this Q vector convergence, and that's the forcing in the Q vector form. So that's all we got for this lab. We'll continue talking about the QG equations in the next couple labs.